Do you sometimes wonder if nuclear fusion can solve our energy problems? What will the initial cost be? And can the grid handle the electricity? I'm Kata. Grab a cup of coffee and let's talk about it. The video consists of 3 parts. First, we're going to debunk some common misconceptions and look at the facts. Then we'll show how it works, including the different types of fusion reactors. And finally, we'll look at where we're at and the progress that's been made. Feel free to use the timestamps to skip to the part of the video you're interested in. If you want to learn more about technology and climate impact, please subscribe below and let's get started. Confusing nuclear fusion and nuclear fission might be the greatest limitation to the success of nuclear fusion. So let's get that out of our systems right away. Nuclear fission power plants have the disadvantage of generating unstable nuclei, which can remain radioactive for millions of years. Nuclear fusion, on the other hand, does not create any long-lived radioactive nuclear waste. And in case of an accident, the worst thing that can happen is that the reactor cools down. A fusion reactor produces helium, which is an inert gas. It also produces tritium in a closed circle within the plant. Tritium is radioactive, a beta emitter to be more precise. However, its half-life is short. Unlike long-lived radioactive nuclei, it cannot produce any serious danger. Unlike nuclear fission, nuclear fusion is not based on a chain reaction.
In a fusion reaction, extreme temperatures and intense pressure cause atoms, typically hydrogen, to fuse together, forming larger atoms. In the process, the atoms lose mass, which is converted into vast amounts of energy. The reaction can produce 4 times as much energy as nuclear fission and nearly 4 million times more energy than burning coal or gas.
The plasma must be kept at very high temperatures with the support of external heating system and must be confined by a magnetic field. Every shift in the working configuration of the plasma can result in the cooling of the plasma. In such case, the reactor would automatically come to a halt within seconds. For this reason, fusion reactors are considered inherently safe.
A tokamak is the most common of current fusion reactors. The reaction takes place in deuterium-tritium plasma. That is, ionized gas consisting of electrons released by the atoms of the deuterium-tritium nuclei. The activation energy is provided by heating the plasma to a temperature of about 100 million degrees centigrade. At this temperature, the wall of the reactor would melt. Therefore, the plasma is kept in motion in a ring-shaped magnetic field. The magnetic field is produced by a toroidal electromagnet. The word tokamak stands for toroidal chamber magnetic coils. A spherical tokamak is based on the same principles as a conventional tokamak. Instead of a ring donut, it looks more like a cored apple. Spherical tokamaks have 4 advantages over conventional tokamaks. They are more efficient because the magnetic field is stronger closer to the center of the ring. They are better at keeping the plasma hotter for longer amounts of time, something scientists call having a higher energy confinement time. They suffer less from instability in the plasma, which could cause heat to leak out or disrupt operation. They have an internal mechanism of producing a stabilizing current more effectively than conventional tokamaks, so the energy input required is lower.
The energy density of nuclear fusion is 4 times more than nuclear fission and 4 million times more than coal or gas. In other words, 2 pounds of fusion fuel can create as much energy as 55 barrels of oil.
The hydrogen can be extracted from seawater, making it a nearly unlimited resource.
Fusion is basically the opposite of conventional nuclear. So in nuclear power, you're splitting a heavy element, and that releases energy, but you end up with the products afterwards, which can be quite hard to handle. Fusion is not a chain reaction, and so there's no possibility for it to run away.
Nuclear fusion does not create any greenhouse gases and is plentiful. That means it's available pretty much everywhere in the world. This all sounds amazing, so what's the deal? The only quote-unquote stretch is that it's not available yet. But before most of you start thinking about the ever-ongoing joke that nuclear fusion is 30 years away and always will be, let's look at the progress that's been made. Over the last 30 to 40 years, the amount of energy that can be produced by a reactor has increased 10,000 times. That's similar to the growth rate of a transistor on a chip. At present, fusion devices create 10 megawatts of fusion power. ITER in the south of France will be capable of producing 500 megawatts of fusion power. This will be on the scale needed for a power station.
ITER, which means the way in Latin, is one of the most ambitious energy projects in the world. ITER originated about 35 years ago at the Geneva Summit. China, the European Union, India, Japan, Korea, Russia, and the United States all are working together to build the world's largest tokamak reactor, the donut-shaped device used for magnetic confinement fusion. Currently under construction, ITER's tokamak reactor will be twice the size of the current largest machine and aims to produce 500 megawatts of fusion power from 50 megawatts of heating power. The actual tokamak reactor is about 20 yards in diameter and about the same height. ITER aims to complete it around 2024, targeting to go nuclear by 2035.
Undoubtedly, sustained fusion is possible in principle. It powers every star in the universe. Making it work on Earth, though, has proved challenging for humanity.
In a so-called stellarator, the magnetic field of the donut is distorted by the outer coils. This is an animation of the magnetic field in Wendelstein 7X in Greifswald. Due to its special design, the stellarator can be adjusted to the particle inclusion and in principle work in continuous operation. How the individual coils are shaped is extremely complex, and calculation was only possible after supercomputers were available. While the tokamak has been researched and developed for a longer time, the stellarator has significant advantages compared to the tokamak. It is both more stable and can be run permanently.
Over decades, nuclear fusion used to be researched and developed by governmental projects such as JET and ITER. For several years now, private companies have started to emerge. Through a combination of new technology and entrepreneurship, some companies hope to beat ITER.
The Canadian company General Fusion, for instance, has raised over 120 million. With about 9 million coming from private investment and 30 million from the Canadian government. General Fusion combines two common approaches in the industry. Inertial confinement, which objects the fusion fuel to extremely high pressure for a brief amount of time, and magnetic confinement, which uses modest pressure for a prolonged time. When heated to extreme temperatures, the fusion fuel becomes a plasma, a state of matter similar to gas except that it contains charged particles that allow it to conduct electricity and respond to magnetic fields.
Our compressor is going to be a big sphere, about 4 meters across, 15 feet across on the inside. And into that big sphere, we are going to put liquid metal. And that liquid metal we're going to spin around in a circle so it opens a hole. And into that hole we're going to put our fuel, which is hydrogen gas. It's preheated up to a few million degrees. And then all around the outside of this sphere is a big array of pistons driven by compressed gas. So they push on the liquid metal and they collapse the hole with this fuel trapped inside. And that collapse happens very quickly and compresses the fuel up to fusion conditions. The peak of the compression, the fuel ignites and gives a fusion reaction. That energy goes into this liquid metal. So the liquid metal heats up. You take this hot liquid metal out, you run it through a heat exchanger and you boil water and make steam. And the steam drives a turbine to make electricity and puts it out on the grid. And we just keep pulsing and do that over and over again.
General Fusion is focused on implementation over research. The company's goal is to build an electricity-generating fusion reactor in the next decade or two.
That's it for now on nuclear fusion. If you got value out of this, I'd very much appreciate if you could subscribe and like below. Let me know what your thoughts are on nuclear fusion, and see you in the next video. Bye!